Have you ever wondered how the universe can expand in every direction and still have no center anywhere at all? It feels impossible. Yet, the deeper we look, the stranger space becomes. There is no hidden heart, no middle point to stand on, only a vast fabric stretching everywhere at once. Tonight, here, in the quiet of Sleepy Traveler, we'll drift through this cosmic puzzle and explore how light, gravity, and motion shape our sense of where here truly is. No pressure to solve anything. Just settle in, breathe softly, and let the universe reveal its quiet truths as you sink into the dark. Long ago, when the universe was only a few 100,000 years old, it was filled with a warm, glowing fog. As that fog cooled, light was finally able to travel freely. A faint echo of that glow still hangs in every direction. It is called the cosmic microwave background, often shortened to the CMB, and it acts like a baby picture of the universe, showing it when it was young and simple. For many years, maps of this ancient light seemed almost perfectly even, with only tiny ripples in temperature. Those soft ripples are important because they are the seeds from which galaxies and stars would eventually grow. This picture was comforting. The universe looked the same in every direction, with no sign of a special place or pattern, just a nearly uniform glow, sprinkled with gentle variations. Then, in the early 21st century, more detailed maps revealed something odd hiding in the speckles. When scientists looked closely, they found a strange alignment in some of the patterns of the CMB. Instead of being completely random, certain features seemed to prefer one particular orientation across the sky. This unsettling hint of order earned a dramatic nickname, the cosmic axis of evil. The name is playful, but it reflects how strongly this pattern challenged the idea of a perfectly directionless universe. The basic idea is simple to picture. Imagine spraying tiny dots of paint on a canvas. You would expect no favored direction, no special tilt, but in the CMB, parts of the pattern appear to lean together, as if an invisible line had guided them. In a universe that was supposed to be the same in all directions, this looked like a quiet whisper of structure where only randomness was expected. At first, most scientists turned to the most down-to-earth explanation. Perhaps it was a mistake. Spacecraft and telescopes, no matter how advanced, still have limits. There could have been tiny flaws in the instruments, subtle issues with how the data was cleaned or combined, or simple statistical flukes that appear when you stare at noisy information for too long. Maybe the axis was just an artifact of our tools, or a coincidence waiting to vanish with better measurements. If that were true, new observations should have smoothed the pattern away. But as different missions used different instruments and methods, the hint of alignment did not entirely disappear. It did not shout. It lingered. That lingering encouraged people to consider more interesting possibilities. Some researchers suggested that very large structures in the universe might be leaving their imprint on the CMB. Imagine immense clusters of galaxies, or even grand filaments of matter stretching across space. Their gravity could gently bend the fabric of space in ways that nudge the ancient light into a preferred pattern. Others turn their thoughts to the invisible ingredients of the cosmos that we already know exist but do not fully understand. Dark matter, which does not shine or reflect light, makes up a bit more than 1/4 of the total content of the universe, holding galaxies together through its gravity. Dark energy, even more mysterious, seems to drive the accelerated expansion of space. If these unseen components can shape the growth of galaxies, perhaps they also sculpt subtle alignments in the CMB that we are only beginning to read. Beyond these ideas lie more speculative suggestions. Our standard picture assumes something called cosmic isotropy, the belief that, on the largest scales, the universe looks the same in every direction. A few physicists have quietly asked, what if this is not perfectly true? What if the cosmos has a faint grain or drift, a built-in direction, as wood has fibers and rings? If isotropy is even slightly broken, then the geometry of the universe might be more intricate than we thought, with gentle asymmetries stretching across the observable sky. From there, imagination wanders toward the possibility of a multiverse, many universes, each with its own properties. In such a setting, the cosmic axis of evil might, in principle, be a subtle echo of something happening beyond our own cosmic horizon, perhaps an interaction with neighboring universes or higher dimensional structures. These ideas are highly theoretical, with no firm proof, but they serve as a reminder that the universe may still hold surprises far beyond our current models. What makes this quiet axis so compelling is the way it touches the foundations of cosmology. For a long time, our understanding has rested on the idea that the universe is roughly the same everywhere and in every direction when you look on very large scales. If the cosmic axis of evil is truly real and not a trick of our measurements, it might mean that this basic assumption needs soft adjustment. The universe would still be mostly uniform, but with a tiny built-in preference that reshapes how we think about its overall structure. This leads us gently back to the question of a center. An alignment in the CMB can feel, at first, like a pointer toward some special line or place. Yet, when all observations are considered together, the broader picture suggests something else. The expansion of the universe does not seem to start from a single central point in space. Instead, it appears to happen everywhere at once, like dough rising in all parts of a loaf, not from one seed in the middle. To understand why this matters, it helps to think about the possible shapes of the universe. On the largest scales, space can curve. Cosmologists often speak of three broad options: flat, closed, and open. These words describe how geometry behaves across cosmic distances, and each one leads to a different story about how the universe moves and evolves. A flat universe is like an endless, perfectly smooth plane. Draw two straight, parallel lines, and they stay the same distance apart forever. The familiar rules of school geometry hold. Triangles behave in the usual way, and space does not loop back on itself. You can travel in any direction without ever returning to your starting point, unless you turn around. A closed universe resembles the surface of a sphere, but in 3 dimensions rather than 2. Think of walking on Earth. If you head straight and never turn, you eventually come back to where you started, even though you never felt a corner. The surface feels boundless, yet it is finite. In a closed universe, space is similar. It is finite, curved, and without edges, so that, in principle, a long enough journey could bring you home again. An open universe can be imagined as a vast saddle shape, curving outward. In such a cosmos, parallel lines slowly drift apart, and distances stretch more and more. The further you travel, the more space seems to widen beneath you. An open universe expands forever, with galaxies growing steadily farther apart as time flows on. To decide which of these shapes best fits reality, scientists again turn to the patterns in the CMB. The tiny hotter and cooler spots in that ancient light act as markers. The apparent size of those spots depends on how space bends. In a flat universe, they show up at a particular characteristic scale. In a closed universe, they look slightly larger than expected. In an open universe, they look slightly smaller. Careful measurements over many years have revealed that the universe is very close to flat. If there is curvature, it is gentle enough that, for almost all practical purposes, space behaves as if it were flat. This near flatness has quiet but deep consequences. In such a universe, expansion continues indefinitely. Galaxies drift farther and farther apart, and over immense stretches of time, many will slide beyond each other's view, their light taking longer than the age of the universe to cross the gap. In a strongly closed universe, by contrast, expansion would eventually slow, stop, and reverse. All matter and energy would be drawn back together in a final collapse, sometimes called a big crunch, a kind of mirror to the Big Bang. This idea once seemed plausible, but current measurements from the CMB and other observations point away from this fate. The universe does not appear to be curved enough to fall back in on itself. An open universe, one that curves outward more strongly, also expands forever. In some versions of that picture, the expansion becomes so dominant that, far in the future, galaxies drift apart, stars burn out, and even atoms might be pulled apart by the relentless stretching of space. The cosmos would grow dark and dilute in a so-called heat death or big freeze, where energy is spread too thinly for new structures to form. Our real universe seems closer to the gently flat case, but its long-term behavior still leans toward endless expansion rather than collapse. Now the idea of a center becomes clearer. In a flat or open universe, there is no single point that can honestly be called the middle. The Big Bang was not like a fireball exploding into empty space from some central location. Instead, it was the beginning of space itself, everywhere at once. A common image is that of dots on the surface of an inflating balloon. Each dot sees all the others moving away. No dot is at the center of the surface. If you were to live inside any galaxy, the others would seem to recede from you, and you would feel as though you were at the middle, but so would every other galaxy. In a closed universe, the idea of a center is even more slippery. Just as the surface of Earth has no preferred central point on the surface itself, a closed three-dimensional universe would not contain its own center. Any true center would lie in a higher dimensional space outside the universe we can experience, like the center of a sphere that is not located on its surface. It is a useful geometric idea, but not a place you could point to in the night sky or ever hope to visit. The fact that our universe appears so close to flat suggests something quietly profound. Space may extend in all directions, without looping back, without edges, and without a true middle. What we can see is only a limited bubble, the observable universe, defined by how far light has traveled since the Big Bang. Beyond that bubble, space likely continues, perhaps without end. In such a vast setting, the notion of a single, privileged center fades away. The expansion we witness is just one part of a much larger, never-ending process, a gentle unfolding with no single heart, yet somehow filled with countless places that can feel like home. Out in that almost endless, centerless space, not everything moves in gentle, predictable paths. Some stars break the pattern. They are flung so hard and so fast that they tear themselves free from their home galaxy and rush out alone into the dark between galaxies. Astronomers call them hypervelocity stars, and they are like cosmic runaways, carrying with them the story of the violent places that threw them out. Most stars live quiet lives, circling within the graceful disks or halos of galaxies, held in place by gravity. Hypervelocity stars are different. Their speeds are so extreme that the pull of their home galaxy is no longer enough to hold them. Once they cross a certain invisible boundary, they are gone for good, set on a path through intergalactic space that may never bring them close to another galaxy again. The first one of these cosmic fugitives was recognized in the year 2005. Astronomers noticed a star now called HV1 moving so quickly that it would not remain bound to the Milky Way. Its speed was measured at more than 1.5 million miles per hour, far beyond what a normal star should have if it were simply orbiting within our galaxy's usual gravitational field. That discovery was like finding a single grain of sand flying out of a calm tide at impossible speed. It forced people to ask, what kind of event could throw a star so violently outward? One of the most powerful explanations leads us straight to the darkest hearts of galaxies. They're supermassive black holes. Most large galaxies, including our own, seem to harbor a giant black hole at their center. The Milky Way's central black hole is called Sagittarius A star. It has a mass of roughly 4 million times the mass of our Sun, all folded into a region so compact that its gravity dominates the crowded core around it. Near such a monster, gravity plays dangerous games. Many stars in the center of a galaxy are not solitary. They live in binary systems, in pairs that orbit each other like dancers circling a shared point. If a binary star system drifts too close to a supermassive black hole, the balance can be shattered. The black hole's gravity grabs one star and pulls it inward, while the other is snapped outward, like the end of a whip. This process is known as the Hill's mechanism, after the astronomer who first described it in this gravitational slingshot. The black hole does not swallow everything. Instead, it trades energy with the stars. One star loses its freedom and falls inward. The other gains an enormous amount of speed, enough to blast out of the galactic center and, in some cases, out of the galaxy itself. It is a strange irony. The same kind of object, famous for trapping even light, can also be the catapult that hurls stars into the deep. The Milky Way's central black hole is a prime suspect for many of the hypervelocity stars we see. One striking example is a star known as S5H VS1, moving at more than 3.7 million miles per hour. When astronomers traced its path backward, like rewinding a film, its trajectory pointed straight toward the galactic center. The story that emerges is simple and dramatic. Once upon a time, it passed very close to Sagittarius A star, lost its companion to the black hole, and was thrown outward on a long, lonely journey. But not every hypervelocity star has to be made by a supermassive black hole. Space can be crowded in other ways too. In dense star clusters, where thousands or even millions of stars share a relatively small region, gravity is constantly tugging and shuffling. Close encounters between stars, or between stars and smaller black holes, can send some members flying out. These interactions are like chaotic dances where partners swap and some dancers stumble out of the room at high speed. The speeds generated this way are usually lower than those from the Hill's mechanism, near a supermassive black hole, but they can still be enough to eject a star from a cluster or even from a galaxy's outer edges. There is also a more explosive route. In a binary system, if one star grows old and massive enough, it may end its life in a supernova, a powerful stellar explosion. When that happens, the sudden loss of mass and the blast of energy can unbind the pair. The surviving companion star, which once moved in a tight orbit, may find itself flung outward, no longer tethered. The speeds produced by this kind of event are often less extreme than those driven by a supermassive black hole, but they can still create fast-moving, runaway stars. In the most dramatic cases, they may contribute to the population of hypervelocity stars. These different mechanisms describe how hypervelocity stars are made, but the stars themselves are more than just curiosities. They are also messengers from regions that are otherwise hard to see. Supermassive black holes, surrounded by dense clouds of gas and dust, can be difficult to study directly. Hypervelocity stars shot out from near these black holes act as tracers of the invisible gravitational landscape they are leaving behind. By measuring a hypervelocity star's speed and direction, astronomers can estimate how close it must have passed to the black hole and how strong the gravitational encounter was. The faster the star, the tighter and more dangerous its former path. When multiple hypervelocity stars are studied in this way, their combined stories help to map the mass and behavior of the central black hole and its immediate environment. It is as if each star carries a small piece of the black hole's signature imprinted in its motion. Once they are ejected, hypervelocity stars travel through the extended halos of galaxies and into the spaces between them. Out there, they are less influenced by the familiar mass of stars and gas, and more by the quiet pull of dark matter and large-scale structures. As they speed through different regions, their paths curve ever so slightly under the influence of these unseen forces. Tracking those subtle bends and shifts can give clues about how dark matter is distributed, where it is denser, and how it shapes the web of structure that spans the universe. There is an even more dramatic possibility, though it is rarer and still under active study. When galaxies collide and merge, the gravitational interactions can become incredibly complex and violent. In such grand encounters, not only individual stars but entire star clusters may be thrown out of their parent galaxies. If such hypervelocity clusters exist, they would be like tight little islands of stars sailing through intergalactic space, witnesses to ancient collisions between galaxies. Finding and studying them would deepen our understanding of how galaxies grow, merge, and reshape themselves over cosmic time. By comparing how many hypervelocity stars or clusters are found in different galaxies, astronomers can also infer how active or turbulent those galactic centers have been. A galaxy with an especially chaotic core, perhaps one that has seen frequent black hole mergers or strong bursts of star formation, might eject more stars than a calmer, more settled galaxy. In this way, hypervelocity stars become a kind of quiet census of past violence. And then there is a softer, almost haunting thought. If some of these runaway stars have planets orbiting them, those planets would be pulled along for the ride. Imagine a small world circling a star that has been hurled out of its galaxy, carried far into the emptiness between galaxies. Such a planet, if it exists, would see no bright band of a Milky Way overhead, no nearby galaxies crowded together on the sky, only a thin, distant scattering of light. With our current technology, these hypervelocity planets would be nearly impossible to detect, but the idea that such lonely worlds might drift in the dark is a reminder of how strange and varied the universe can be. From these racing stars and their possible hitchhiking planets, our attention can turn to something older and more silent: black holes that may have been present from the very beginning. Among the many ideas in cosmology, primordial black holes stand out as one of the most ancient and intriguing. Unlike the black holes we know that form from the deaths of massive stars, primordial black holes could have been born in the first instance after the Big Bang itself. Their story begins in a universe that was young, hot, and incredibly dense. In those first fractions of a second, everything was a roiling soup of particles and energy, flickering and fluctuating on very small scales. Tiny regions could, for brief moments, become denser than their surroundings. If a region became dense enough, gravity could overwhelm the forces trying to smooth things out, and that pocket of matter and energy could collapse in on itself, forming a black hole almost immediately. This is very different from what happens today when a star dies. Stellar black holes form only after a massive star has spent millions of years burning its fuel and finally collapses. Primordial black holes would have needed no such long preparation. They could have appeared almost instantaneously, fed not by slow stellar evolution but by the wild fluctuations of the newborn cosmos. Because they formed in such a different way, primordial black holes could come in a much wider range of sizes. Some theories suggest that the smallest of them might have been tiny, with masses much lower than that of a typical star, perhaps comparable to mountains, or even less, though still incredibly dense. Over time, the smallest ones may have evaporated entirely through a process called Hawking radiation, a quantum effect that slowly lets black holes lose mass and energy. Others, however, could have been far larger, with masses equal to thousands of suns, formed from slightly bigger dense patches in the early universe. These heavier primordial black holes would still be out there today, hidden in the darkness, difficult to distinguish from black holes born from dying stars or from the giant black holes in galactic centers. What makes them special is not how they look now, but when and how they may have formed. Not as the end of a star's life, but as some of the first heavy objects to condense out of the early universe's chaos. The formation of primordial black holes depends sensitively on the pattern of density fluctuations that filled the early cosmos. Those fluctuations themselves were likely stretched and shaped by a rapid expansion phase called inflation, during which space ballooned outward at an extraordinary rate. In most places, the ripples in density were small enough that the universe smoothed out into the familiar pattern of galaxies and clusters we see today. But in a few regions, if the ripples were stronger, gravity could have taken over and forced a collapse. Because these black holes could have formed on scales much smaller than galaxies, they offer an especially flexible tool for cosmologists. Some could be tiny, some could be as heavy as many thousands of suns. The most massive primordial black holes might help to explain how supermassive black holes at galactic centers grew so quickly. Others might lurk in the spaces between stars and galaxies, invisible unless they pass in front of a background star and bend its light, or interact with matter in ways we can detect. In this way, primordial black holes act as a bridge between the earliest moments after the Big Bang and the large-scale structure of the universe we see now. They carry with them whispers of those first violent instants, and some of them, if they exist in the heavier ranges, could rival supermassive black holes in size. Their ability to form so early and on such tiny scales means primordial black holes might once have been almost everywhere, sprinkled through the young universe like invisible seeds. Even if most were small, their combined gravity could have tugged on the surrounding gas and dust, nudging matter into clumps that over time, grew into the first stars and galaxies. In that sense, these ancient black holes may have helped sketch the first outlines of the cosmic scenery we see today. If they were numerous, primordial black holes could act as hidden anchors scattered through space, quietly shaping how matter is arranged on the largest scales. Where there are more black holes, gas and dark matter would find it easier to gather, forming denser regions. Where there are fewer, space might stay more empty. The grand web of filaments and clusters that stretches across the universe could, in part, have been guided by their silent pull. One of the most tempting ideas is that primordial black holes might be connected to dark matter, the unseen substance that outweighs ordinary matter by a large margin. Dark matter does not shine, absorb, or reflect light, so telescopes cannot see it directly, but its gravity tugs on stars and galaxies, holding them in place. Astronomers estimate that roughly 85% of all matter in the universe is this invisible kind. Some scientists have wondered whether a portion of that hidden mass could simply be made of many small, ancient black holes. If primordial black holes are common enough and have the right range of masses, they could contribute to the missing mass we attribute to dark matter. The trouble is that these objects are, by their very nature, hard to find. Black holes formed from dying stars often betray themselves. When they pull in gas from a companion star or from their surroundings, the infalling material heats up and emits high-energy radiation such as X-rays. Primordial black holes, especially if they are small or drifting through relatively empty space, might not have such bright companions. They could slip through the cosmos almost entirely in shadow. To hunt for them, astronomers turn to more subtle tricks. One is called gravitational lensing. When a massive object passes in front of a distant star, its gravity bends the light, and the background star may briefly appear brighter or slightly shifted. If primordial black holes are sprinkled through our galaxy, some of them should occasionally drift across our line of sight, producing tiny, temporary changes in brightness. By watching huge numbers of stars and looking for these flickers, scientists hope to catch the footprints of otherwise invisible black holes. Even so, such signals are faint and rare. Another avenue lies in listening rather than looking. When black holes collide and merge, they shake the fabric of space-time itself, sending out ripples called gravitational waves. Detectors such as LIGO, the Laser Interferometer Gravitational Wave Observatory, have already recorded the mergers of black holes with masses similar to those expected from massive stars. If some merging pairs turn out to have unusual masses or patterns that fit better with primordial black holes, that would be an important clue. In this way, primordial black holes are not just exotic possibilities, they are also potential messengers from the infant universe, carrying hints about how lumpy or smooth it was and whether there were special regions where gravity briefly gained the upper hand. Their distribution across space could reveal whether matter was laid out in a way that favors certain regions over others, and whether this pattern has anything to do with our sense that some directions seem more structured than others when we look at the universe on its largest scales. From these ancient gravitational seeds, the story drifts towards something even more elusive: the energy of empty space itself. The phrase vacuum energy sounds almost contradictory. A vacuum is supposed to be empty, and yet, in the quantum view of reality, even the emptiest space is restless. It seethes softly with activity that we cannot see directly, like a lake whose surface looks calm while currents move quietly below. According to quantum mechanics, there is a built-in uncertainty to the world. The Heisenberg uncertainty principle says that the position and momentum of a particle cannot both be known with perfect precision at the same time. This fuzziness means that even in a perfect vacuum, fields and particles cannot sit completely still. Instead, they flicker in and out of existence as so-called virtual particles, appearing for tiny moments and then annihilating one another. During their brief lives, these virtual particles carry energy. When you add up the effects of countless such flickers in every tiny region of space, you find that the vacuum is not truly empty. It has an energy of its own, spread throughout the universe. This is what physicists call vacuum energy. One of the clearest hints that this energy is real comes from an experiment known as the Casimir effect. When two very thin metal plates are placed extremely close together in a vacuum, they experience a tiny attractive force because the quantum fluctuations between the plates are slightly different from those outside them. Vacuum energy would already be fascinating as a feature of quantum theory, but it may also be tied to something far larger, the way the universe itself expands. Astronomers have found that not only is the universe expanding, the expansion is speeding up. Galaxies are not just drifting apart, they are doing so faster over time. To account for this, cosmologists speak of dark energy, a mysterious component that makes up about 68% of the total energy content of the universe and acts as a kind of gentle anti-gravity on cosmic scales. One leading idea is that dark energy might simply be the energy of the vacuum itself. If empty space has an energy density that does not dilute as the universe expands, then, as space stretches, the total amount of this energy increases and its repulsive effect becomes more important. In this picture, vacuum energy is not an odd detail. It is the dominant influence on the future of the cosmos. Long before the term dark energy was widely used, Albert Einstein introduced something similar in his equations of general relativity, the cosmological constant. He imagined it as a property of space that could counteract gravity and keep the universe static. When later observations by Edwin Hubble showed that the universe is actually expanding, Einstein reportedly called the cosmological constant his greatest mistake. Yet, decades later, the idea returned. A positive cosmological constant behaves like a uniform vacuum energy, pushing space to expand at an accelerating rate. If vacuum energy, expressed through something like a cosmological constant, really is driving the accelerated expansion, it has deep implications for the fate of everything. One possible future is quiet and slow. If the vacuum energy stays constant, the universe will continue to expand forever. Galaxies will drift farther and farther apart until, in the far future, each one becomes an island of stars surrounded by increasing darkness. Stars will age and die. New stars will form more slowly, and eventually the cosmos will grow cold and thin, a scenario often called the heat death or big freeze. But the story might be more complicated. If vacuum energy can change over time, then dark energy might grow weaker or stronger. If it weakens enough, gravity could eventually win, slowing the expansion and perhaps reversing it. In such a case, the universe might begin to contract, with galaxies moving closer together and densities increasing until everything collapses into a final state, sometimes called a big crunch. There is also a more dramatic possibility, called the Big Rip. In that vision, the energy of the vacuum does not stay constant, but increases as space expands. The repulsive effect of dark energy becomes stronger and stronger, first tearing galaxies away from each other, then unbinding planetary systems, and finally overcoming even the forces that hold atoms together. In the last moments, every structure in the universe would be pulled apart by the acceleration of space itself. Each of these futures depends on the properties of vacuum energy, something we still do not fully understand. Yet, even with all this uncertainty, one thing is clear. Whatever empty space is, it is not simple. It shapes the motion of galaxies, the fate of stars, and the story of the universe. For a long time, astronomers thought they had a tidy picture of how matter moves on the largest scales. Galaxies, carried along by the general expansion of space, should recede from one another in all directions, except where local gravity from nearby galaxies or clusters pulls them into smaller patterns. Against this background, each region would have its own swirls and eddies, but nothing too surprising. Then, in the late 2000 decade, something odd appeared in the data. By studying the motion of distant clusters of galaxies, some researchers noticed that many of these clusters, spread across a huge portion of the sky and located billions of light years away, seemed to share a common drift. They were all moving in the same general direction, as if drawn toward a point beyond the part of the universe we can see. This puzzling motion was given a name: the dark flow. These galaxy clusters, some of the most massive structures in the cosmos, appeared to be moving at unusually high speeds, on the order of several hundred to around 1,000 kilometers per second, all headed along a similar path. What made it particularly strange was that this motion was not random, but coherent across a vast region of space, suggesting that something was pulling these clusters in the same direction. This strange shared motion, this dark flow, does not sit comfortably inside the neat picture we have built for how galaxies should behave. In the standard view, the universe is expanding, pushed on large scales by dark energy. Everything is, on average, moving away from everything else. Local gravity can pull galaxies into clusters or tug them toward a nearby neighbor, but over vast distances the motion should even out, with no single distant point acting like a cosmic drain. Yet the clusters caught in the dark flow seem to be drifting toward a place we cannot see, somewhere beyond the edge of our observable universe. It is as though they are feeling the pull of a hand that never appears in the frame. Whatever lies in that unseen direction, if the effect is real, it is strong enough to tug on some of the most massive structures we know, across billions of light years of space. One gentle way to think about this is to imagine that our observable universe is only part of a much larger landscape. Within the part we can see, we already know that matter is not spread evenly. There are galaxy clusters, superclusters, and long filaments of dark matter that weave together into a vast, three-dimensional web. Gravity shapes this web, pulling matter into knots and strands over cosmic time, but the region we can observe is limited by how far light has had time to travel since the Big Bang. Beyond that horizon, the universe may continue in ways we can only infer. In that larger, hidden expanse, there might be enormous structures, even more massive clusters or concentrations of dark matter that never send us their light. If such an unseen attractor exists just beyond our cosmic horizon, its gravity could still reach inward, ever so slightly, drawing galaxy clusters toward it. The dark flow might then be the visible part of this deeper tug, like leaves on the surface of a pond moving towards something heavy resting on the bottom. Some researchers imagine this unseen attractor as a supercluster of galaxies, or a region where dark matter is especially dense. Others let their thoughts wander further and wonder whether the pull could come from something even stranger, perhaps from another large region of space with different properties, or even from another universe entirely. In that picture, our cosmos would be just one bubble in a larger multiverse, and the dark flow would be a faint sign of gravitational whispers leaking across the boundary between bubbles. All of this is thrilling, but also unsettling, because it stretches our current models of cosmology close to their limits. The standard model assumes that, on large enough scales, the universe is homogeneous and isotropic, roughly the same everywhere, and the same in every direction. This idea, called the cosmological principle, underpins many of our calculations. If there truly is a preferred direction, a large-scale flow towards some distant attractor, then the universe may be more lopsided than we thought. Of course, not everyone is ready to accept such a dramatic conclusion. Many scientists point out that measurements at these scales are delicate. Extracting the motions of distant clusters from faint data is complicated. Tiny biases in how we collect, clean, and interpret the signals can produce patterns that look meaningful but are not. In this view, the dark flow may yet turn out to be a mirage born of imperfect instruments or incomplete corrections. But the fact that hints of the dark flow have appeared in more than one analysis makes it hard to dismiss entirely. It leaves us in a familiar place, suspended between competing possibilities, listening closely to the data while knowing that our picture of the universe might still be missing important pieces. One of those missing pieces belongs to an oddly personal puzzle, the question of where all the ordinary matter has gone. When you touch a table, feel your own skin, or look at a star, you are meeting baryons, the particles that make up protons and neutrons, and thus the nuclei of atoms. Every rock, cloud, planet, and living thing is built from them. For something so familiar, ordinary matter behaves in an oddly elusive way when we look at the universe as a whole. From our understanding of the Big Bang and the physics of nuclear reactions in the early universe, we can estimate how many baryons should exist. The theory, supported by observations of the cosmic microwave background and the abundances of light elements, tells us how much ordinary matter should have been produced in those first hot moments. But when astronomers tally up all the baryons they can see today, in stars, gas clouds, and galaxies, they find only about half of what should be there. The rest seem to be missing. To make sense of this, it helps to separate the missing baryons from dark matter. Dark matter is a different kind of mystery. It is not made of protons and neutrons, does not interact with light in the usual way, and accounts for the majority of matter in the universe. The missing baryons, by contrast, are ordinary matter we believe must exist but simply do not see. They should behave like normal gas, but they appear to be hiding. One promising idea is that these baryons never settled into bright stars or dense glowing clouds. Instead, they may be spread out as a very thin, very hot gas that fills the spaces between galaxies. This gas would be so diffuse and faint that it barely shines, especially in visible light. It would still contribute mass and feel gravity, gently shaping the motion of galaxies and clusters, but it would be nearly invisible to the telescopes we have relied on for most of our cosmic inventory. To picture where this gas might live, we can return to the idea of the cosmic web. On the largest scales, matter in the universe is arranged not like a random sprinkle of dots, but like a network of filaments and nodes. Dark matter forms the backbone, with galaxies and clusters sitting like bright beads along the strands. Between these bright knots, filaments of gas and dark matter stretch across huge distances, connecting structures and defining vast, empty-looking voids. The missing baryons are thought to be lurking in these filaments, in a state called the warm-hot intergalactic medium. The gas there may be heated to millions of degrees, which sounds intense, but because it is spread over such enormous volumes, it remains very faint. It does not glow brightly in the ways we are used to seeing. Instead, its presence must be inferred through more delicate traces. One such trace comes from quasars, those extremely bright, distant beacons powered by supermassive black holes at the centers of young galaxies. The light from a quasar travels through great stretches of space before reaching us. Along the way, it passes through clouds and filaments of gas. Each time it does, specific wavelengths of the quasar's light are absorbed by the atoms in that gas, leaving narrow, dark lines in the spectrum. By carefully studying these absorption lines, astronomers can detect gas that would otherwise be invisible. Some of the missing baryons show their presence in this way as quiet fingerprints in the light of background quasars. The pattern suggests that there are indeed large amounts of ionized gas stretched between galaxies, lying along the filaments of the cosmic web. Another piece of evidence comes from X-ray observations. Gas that is hot enough can emit X-rays, faint but detectable if one looks with sensitive instruments from space above Earth's atmosphere. Telescopes such as Chandra and XMM Newton have detected dim X-ray emission coming from the regions between galaxy clusters, supporting the idea that hot, diffuse gas resides there. This gas does not form stars or bright nebulae, but it may account for a substantial fraction of the missing baryons. If so, the missing baryon problem becomes less a mystery of absence and more a matter of misplacement. The baryons are not gone. They are simply not where we first thought to look. Many of them never settled into galaxies at all, but remained in the filaments of the cosmic web, serving as a hidden reservoir that feeds galaxies over time. As gas flows along these strands, it can fall into galaxies, fueling new waves of star formation and helping to shape how galaxies grow and change. The filaments themselves, woven from dark matter and threaded with this faint gas, form a kind of scaffolding for the universe. When we map the positions of galaxies on large scales, we see that they are not scattered evenly. They cluster along these strands, gather at their intersections, and leave vast voids in between. The missing baryons, distributed along the filaments, help to explain why galaxies follow these patterns, rather than being randomly sprinkled across space. Even with these advances, the search is not complete. Not all of the expected baryons have been firmly accounted for, and there may still be reservoirs of cooler, less ionized gas or matter hiding in the outskirts of galaxies where our instruments are less sensitive. The picture grows clearer with each new observation, but some pieces are still soft around the edges. And then, just as filaments mark where matter gathers, there are places where almost nothing gathers at all. In the grand, intricate lattice of galaxies and clusters, some regions stand out for their startling emptiness. These are known as cosmic voids, vast stretches of space with far fewer galaxies than average, like deep hollows carved into the cosmic web. Among them, astronomers have identified especially large and striking examples, such as the region sometimes called the Adenese supervoid, a reminder that in the universe, emptiness can be just as telling as light. Out in the quiet hollows of the cosmic web, Some empty regions are more than just gaps between galaxies. One of the most intriguing is a gigantic stretch of space that appears unusually empty and, in a subtle way, unusually cold. Astronomers call it a supervoid, and it happens to lie in the same direction as one of the strangest features in the cosmic microwave background, a cold spot that should not, by our simple models, be quite so cold. The cosmic microwave background, that ancient afterglow of the Big Bang, is astonishingly smooth. Its temperature is almost the same in every direction, with only tiny ups and downs that mark where the early universe was slightly denser or thinner. Those gentle ripples were the seeds from which galaxies and clusters grew. Against this calm pattern, one patch stands out, a region in the direction of the constellation Eridanus that is noticeably colder than its surroundings and larger than our standard theories comfortably predict. Finding a vast underdense region of space, a supervoid, in the same direction offers a tempting clue. Voids are not unusual. The universe is full of them. Great cavities between the filaments and clusters of the cosmic web, where there are far fewer galaxies than average. They can stretch for hundreds of millions of light years. But this particular supervoid seems especially large, and its alignment with the cold spot suggests the two might be linked. The possible connection rests on the way light responds to gravity as it travels. As photons from the cosmic microwave background cross the universe, they pass through regions with different amounts of matter. In places where matter is dense, gravity is stronger, and the space-time valley is deeper. In voids, the valley is shallower. When photons fall into a gravitational well, they gain energy and are slightly blue-shifted. As they climb back out, they lose that energy again and become slightly red-shifted. In a perfectly static universe, what they gain on the way in, they lose on the way out. But our universe is expanding, and that expansion can change the depth of the gravitational wells and hills, while the photons are inside them. In the case of a supervoid, as space continues to expand and the void evolves, the photons can lose a little more energy climbing out than they gained falling in. This subtle imbalance, part of what is called the Sachs-Wolf effect, can leave the photons slightly cooler when they reach us, making that patch of the cosmic microwave background appear colder. For the Eridanus supervoid, its sheer size might amplify this effect. Cosmic microwave background photons crossing such a vast, underdense region would experience this uneven trade of energy over an especially long distance, leading to the pronounced cold spot we see. It is an elegant story. A great emptiness carved into the cosmic web leaves a faint chill imprinted on the oldest light in the universe. And yet, the numbers do not fall into place quite perfectly. Some calculations suggest that the Sachs-Wolf effect from even such a large void may not be enough by itself to explain the entire depth of the cold spot. That opens the door to more intricate possibilities. Perhaps the supervoid is part of a larger chain of connected voids, a kind of superstructure in the cosmic web that we have not fully mapped. Or perhaps there are additional, more exotic influences layered on top of the gravitational effect of emptiness. A few speculative ideas go further still, hinting that the cold spot might be a scar from something outside our usual picture of the universe. In some versions of multiverse theories, our universe is just one bubble among many. If bubbles can collide or interact, such an encounter could, in principle, leave a mark, an unusual patch in the cosmic microwave background, colder or hotter than expected. The alignment of the cold spot and the supervoid has led some to wonder whether both might be pieces of a larger, stranger story involving dark energy, unusual distributions of matter, or even contact with neighboring universes. These ideas are highly tentative, but they remind us how much room for surprise still exists. Even without venturing into the multiverse, voids themselves are valuable laboratories. In dense regions like galaxy clusters, gravity is strong and complex, and many different processes compete. In voids, matter is sparse, and the gentle push of dark energy can show its effects more cleanly. By studying how galaxies sit around the edges of voids, how they move, and how light from the cosmic microwave background is altered as it passes through, scientists can test models of dark matter, dark energy, and gravity in environments very different from crowded galaxy centers. Voids, however, are hard to find precisely because they are defined by absence. To detect a structure like the Eridanus supervoid, astronomers must map the positions of many galaxies in a region of sky and look for an unusually large patch where the population thins out. It is like noticing a quiet clearing in a forest, not because the clearing shines, but because there are fewer trees. Careful surveys have revealed such a clearing in the direction of the cold spot, lending weight to the idea that emptiness itself is part of the explanation. These vast, hollow regions and delicate temperature patterns bring us back to a deeper puzzle at the heart of the universe's story: how matter itself came to dominate. The cosmic microwave background tells us about the early universe as a nearly smooth soup of radiation and particles. According to our best theories of particle physics, that newborn universe should have produced matter and antimatter in almost perfect balance. For every proton, there should have been an antiproton. For every electron, a positron. Matter and antimatter are like mirrors of each other. When they meet, they annihilate, turning into pure energy. If the early universe had been perfectly symmetric, matter and antimatter would have destroyed each other completely, leaving behind a bath of radiation but almost no solid stuff from which to build stars, planets, or people. And yet, here we are, in a universe filled with matter and almost no large regions of antimatter. Something must have tipped the scales. The process that produced this tiny but crucial imbalance is called baryogenesis, the creation of more baryons, particles like protons and neutrons, than antibaryons. The difference did not need to be large. For roughly every billion pairs of baryons and antibaryons that annihilated, it seems there was about one extra baryon left over. That small surplus is enough to form all the visible matter in the cosmos. The question is how the universe managed to favor matter, even slightly, in its earliest moments. To frame the conditions needed for this to happen, the physicist Andrei Sakharov outlined 3 requirements. The first is that the laws of physics must allow processes that can change the total number of baryons. Normally, many interactions conserve baryon number, meaning the total count of baryons minus antibaryons stays the same. For an imbalance to appear, there must be reactions that can create or destroy baryons in a way that is not perfectly balanced by their antiparticles. The second requirement involves symmetry, specifically something called CP symmetry, which combines charge, conjugation, and parity. Roughly speaking, CP symmetry says that particles and antiparticles should behave in mirror image ways. If this symmetry were exact, any process creating extra baryons would be matched by an equivalent process creating extra antibaryons. To tilt the universe toward matter, CP symmetry has to be slightly broken, allowing matter and antimatter to be treated just a bit differently by the laws of physics. The third condition is that the universe must be out of thermal equilibrium while these processes occur. In full equilibrium, creation and destruction processes balance out, and any temporary difference in baryon number would be washed away. The early universe, however, was expanding and cooling rapidly, passing through transitions where conditions changed faster than some reactions could keep up. In these non-equilibrium moments, small asymmetries could freeze in and survive. Together, these three requirements, the possibility of baryon number violation, CP violation, and departure from equilibrium, are known as the Sakharov conditions. They provide a kind of map for how baryogenesis might have unfolded, but they do not specify exactly which particles and interactions were responsible. That remains one of the deepest open questions in cosmology and particle physics. One promising setting for baryogenesis is the electroweak phase transition, a brief period when the universe was still extremely young, less than a tiny fraction of a second old, at unimaginably high temperatures. What we now think of as the electromagnetic force and the weak nuclear force were unified. As the universe expanded and cooled, these forces separated, and the fields associated with them settled into new configurations. During this transition, bubbles of the new phase could have formed and grown, providing environments out of equilibrium where Sakharov's conditions might be satisfied. The standard model of particle physics does include some CP violation, observed in the behavior of certain particles, like neutral kaons and B mesons, but calculations suggest that the amount of CP violation in the standard model is far too small to generate the observed matter-antimatter imbalance. This shortfall has pushed researchers to explore theories that go beyond the standard model, such as supersymmetry, which introduces a host of new particles and interactions. Some of these new ingredients could provide the extra CP violation and baryon number violation needed to produce the right amount of asymmetry. Another elegant idea is leptogenesis, which shifts the focus from baryons to leptons, the family of particles that includes electrons and neutrinos. In leptogenesis, an asymmetry between leptons and antileptons is created first, perhaps through the decays of very heavy neutrinos in the hot early universe. This lepton asymmetry can then be partially converted into a baryon asymmetry through processes that violate both lepton number and baryon number, but preserve certain combined quantities. In this way, a tiny imbalance in the lepton sector ultimately becomes the surplus of matter that builds galaxies and stars. Leptogenesis is especially appealing because it connects baryogenesis to the puzzling nature of neutrinos. Neutrinos are incredibly light and interact only weakly, making them difficult to study, yet they may hold the key to why anything exists at all in its present form. If we can better understand their masses and how they mix between different types, we may gain clues about what happened in those first instants after the Big Bang. All of these ideas, electroweak, baryogenesis, supersymmetric extensions, leptogenesis, are attempts to reconstruct events that took place when the universe was still a roiling, high-energy sea of elementary particles. In that brief, intense window, conditions were unlike anything we can recreate on Earth, except in glimpses at powerful particle colliders. As the universe expanded and cooled, these exotic processes shut down, leaving behind the quiet, stable matter we know. Whatever mechanism finally turns out to be correct, the imbalance between matter and antimatter that gave rise to our world must have been forged during that early, fleeting era of incredibly high energy. Some researchers have wondered whether the universe's brief burst of inflation, that astonishingly fast expansion in its first moments, helped set the stage for the imbalance between matter and antimatter. Inflation smoothed the cosmos on large scales, ironing out wrinkles and evening out densities. But it also drove regions far from thermal equilibrium, exactly the kind of uneven state in which tiny asymmetries can freeze in instead of being washed away. In those fleeting, overstretched instants, the conditions Sakharov described could have been quietly satisfied, allowing a small excess of matter to take root. Even if inflation helped, another gentle question remains. Did this process unfold the same way everywhere? Or did some regions of the early universe experience it more strongly than others? If baryogenesis happened uniformly, then the matter-antimatter imbalance would have arisen in much the same way throughout the cosmos. Every patch of space would have been given the same small tilt toward matter. But if the conditions for baryogenesis were met more strongly in some locations than others, then certain regions might have ended up with a slightly larger surplus of matter. That raises the possibility of a universe where the imbalance is a little patchy, where some cosmic neighborhoods are more matter-rich than others, and where the processes that favored matter might, in some subtle way, trace back to specific events or structures. To picture this, some scientists have explored the idea of topological defects, special structures that could have formed as the universe cooled and its fields settled into new patterns. These defects have names that sound like threads and walls from a dream, such as cosmic strings and domain walls. If they formed during phase transitions in the early universe, they might have acted as focal points where conditions differed from the surroundings. In those regions, baryogenesis could have been more intense, creating local pockets of excess matter. There is little direct evidence that such defects exist in large numbers, and they remain speculative. Yet they offer an appealing way to imagine the early cosmos not as perfectly uniform, but as a place where certain lines and boundaries shaped how the matter-antimatter story unfolded. Even so, when all the models are laid side by side, most still suggest that baryogenesis was, in broad strokes, a universal process. It would have been driven by the same fundamental forces and interactions everywhere, in harmony with the cosmological principle, the idea that, on the largest scales, the universe is homogeneous and isotropic, with no special place or special direction. To tease out which of these possibilities is closest to the truth, physicists listen both to the very large and the very small. On Earth, high-energy particle accelerators, such as the Large Hadron Collider, recreate for brief moments the temperatures and energies that existed just after the Big Bang. In those controlled collisions, new particles flash into existence and decay, revealing hints of new symmetries and new ways in which they might be broken. Researchers look especially carefully for additional sources of CP violation beyond what the standard model predicts that could have tipped the universe toward matter more decisively. At the same time, astronomers turn their instruments outward, studying the large-scale structure of the cosmos, the way galaxies are arranged, and the behavior of particles like neutrinos. Neutrinos, with their ghost-like ability to pass through almost everything, may carry crucial information about the early universe's imbalances. Their tiny masses and the way they change from one type to another could be linked to leptogenesis and the transfer of asymmetry from leptons to baryons. In this way, the path from a neutrino detected in a quiet underground lab can lead back to the first instance after the Big Bang. From this delicate dance of particles and fields, our attention can drift to another, more classical idea, the notion of a center of mass. In physics and astronomy, the center of mass, or barycenter, is the point where all the mass in a system balances. It is not always located inside a single object. In the case of Earth and the Moon, for example, the barycenter lies beneath Earth's surface, but not at its exact center. Both bodies orbit this shared point, tracing gentle motions around it. In our solar system, the same idea applies on a grander scale. The sun does not sit perfectly still. The combined pull of the planets, especially the giant ones like Jupiter and Saturn, causes the sun to wobble around the solar system's barycenter. Sometimes this point is inside the sun, sometimes just outside its surface, but it is always the place where the mass of the entire system can be thought of as balanced. We can carry this concept outward to galaxies and clusters. A galaxy's stars, gas, and dark matter halo all together define a barycenter around which individual components move. In a cluster of galaxies, each galaxy orbits within the shared gravity of the whole group. By summing up all the mass and its positions, we can define a center of mass even when no single bright object sits precisely at that point. It is tempting, then, to ask whether the universe itself has such a barycenter. If we could somehow gather the positions and masses of all galaxies, all clusters, all dark matter, and all other forms of energy, would there be a single cosmic balance point, the place where all the mass of the universe effectively centers? The idea is captivating, but it runs into deep complications. First, the universe is not a simple, bound system like a planetary system or a galaxy. It is expanding, with the distances between most galaxies increasing over time as space itself stretches, driven largely by dark energy. This expansion means that galaxies are not only moving because of their mutual gravitational pulls, they are also being carried along by the growth of space. Any attempt to define a cosmic barycenter would have to account for both these motions at once. Second, matter in the universe is not gathered into one central lump. Instead, it is spread out in the cosmic web. Galaxies group into clusters, clusters into superclusters, all linked by filaments of dark matter and separated by vast voids. There is no special central knot where everything is densest. Rather, there are many dense regions scattered across space. The pattern is intricate and multi-layered, without an obvious heart. In smaller systems, we can lean on the fact that the total mass and the distances between objects are relatively well known. In a two-body system, the barycenter is simple to calculate. In a system of many bodies, we can still compute it by adding up the contributions from each mass. But when we step up to the scale of the entire observable universe, the task becomes almost unreal. We have to contend with dark matter, which makes up about 85% of the matter content and is invisible except through its gravity, and with dark energy, which behaves more like an energy of space itself than like a collection of particles. Dark matter complicates the picture because it is spread out in extended halos around galaxies and clusters and along the filaments of the cosmic web. To define a true cosmic barycenter, we would need to include not just the luminous matter we can see, but all of this unseen mass as well. Dark energy complicates things further by driving the expansion, contributing to the overall energy budget of the universe in a way that does not clump like ordinary matter. Even if we set aside dark energy for a moment and focus only on matter, the expansion makes any cosmic barycenter a moving target. As galaxies drift, merge, and fall into new structures, the point where all their masses balance would shift over time. On very long timescales, it might not make sense to speak of a single, permanent center at all, only of a balance that evolves as the universe does. Most modern cosmological models, guided by the cosmological principle, suggest that there is no unique center of the universe. The universe, on large scales, looks roughly the same in every direction from any vantage point. There is no special location from which everything is expanding. Rather, the expansion is happening everywhere at once. In such a picture, talk of a global barycenter begins to lose its usual meaning. Still, there may be regions that behave like temporary attractors. If matter is not distributed perfectly evenly, there will be areas where its density is higher. These overdense regions can draw in galaxies and clusters from their surroundings. On very large scales, entire superclusters may be slowly migrating toward particularly massive zones, some of which may even lie beyond the edge of the observable universe. The motions we observe, such as the dark flow, hint that there may be deep gravitational wells outside our view, gently steering the motions within it. If such massive, unseen structures exist, they could, in a loose sense, influence where a kind of shifting cosmic barycenter might lie at any given moment. But that point would not be a fixed absolute center. It would be a moving average, a balance that changes as galaxies stream along the filaments of the cosmic web, and as dark energy continues to stretch the space between them. Trying to define a barycenter for the entire universe, then, is as much a philosophical exercise as a physical one. It invites us to think about how we picture the cosmos, whether we imagine it as something that must have a middle, or whether we can grow comfortable with a universe that is everywhere and nowhere centered at once. And while we wrestle with that image, another quiet process waits in the background, touching some of the most extreme objects we know. To understand how even black holes might slowly fade over unimaginable timescales, we turn to a phenomenon called Hawking radiation, the gentle evaporation of black holes in the universe's core. When people first imagined black holes, they pictured them as perfect traps, silent pits in space-time from which nothing, not even light, could ever escape. Then, in the early 1970s, Stephen Hawking showed that this picture was not quite complete. By bringing quantum mechanics into the shadowed region near a black hole's edge, he found that black holes are not entirely black. They can glow very faintly with a kind of ghostly warmth that slowly eats away at their mass. This gentle leak of energy is what we now call Hawking radiation. The idea begins with the strange restlessness of the quantum vacuum. Even in what seems like empty space, particle and antiparticle pairs are constantly flickering into and out of existence, borrowing energy for a moment and then giving it back as they annihilate each other. Most of the time this happens unnoticed, a quiet background hum. But near the event horizon of a black hole, the boundary that marks the point of no return, gravity can interfere with this dance. If a virtual particle pair appears right at the edge, the intense gravitational field can sometimes pull them apart. One member of the pair falls inward, crossing the horizon and becoming part of the black hole. The other escapes outward, no longer able to reunite and annihilate. To a distant observer, that escaping particle looks like radiation coming from the black hole itself. Because energy must be conserved, The black hole effectively loses a tiny bit of mass each time this happens. For a large black hole, such as one formed from a massive star, the effect is unbelievably slow. The temperature associated with Hawking radiation is incredibly low, and the rate of mass loss is so small that it would take far longer than the current age of the universe for such a black hole to evaporate. On human timescales, they might as well be eternal. But for much smaller black holes, the story changes. The smaller the black hole, the stronger the quantum effect, and the more intense the radiation. Tiny black holes would evaporate more quickly, shining briefly, and then fading away. This is where primordial black holes become especially interesting. If black holes formed in the very early universe from small, dense patches of matter, some of them might have started out with masses far lower than ordinary stellar black holes, perhaps comparable to large asteroids, or even less. Over billions of years, Hawking radiation could have eaten away at them, causing some to vanish completely and others to approach their final, rapid blaze of evaporation today. The radiation from such events, if we could detect it, would carry information from the earliest times, like a last whisper from the universe's childhood. Evaporating black holes sit at the crossroads of our two great theories: quantum mechanics, which describes the very small, and general relativity, which describes gravity and the very large. Hawking radiation emerges when we let quantum fields live in the curved space-time around a black hole. Studying its properties, even in theory, helps us probe how these two frameworks might eventually be woven into a single, deeper description. In that sense, each evaporating black hole is a tiny laboratory for a future theory of everything. There is also a quieter, more cosmic angle. If primordial black holes exist in significant numbers, some of them might reside in dense regions, such as galaxy clusters or the halos of dark matter that surround galaxies. Their evaporation could, in principle, leave faint signatures that betray where they are hiding. In crowded environments near supermassive black holes, evaporating primordial black holes might help map how matter is arranged, hinting at the shapes of dark matter halos and the gravitational structures that hold galaxies together. The Hawking glow of these tiny objects could thus become a tracer of invisible mass. From the edges of black holes, where quantum flickers steal energy from darkness, our attention can drift to another kind of exotic possibility: particles that carry a single magnetic charge. In everyday life, magnets always come with two poles. North and south break a magnet in half, and each piece still has both poles. No matter how small the fragments, they stubbornly keep their paired nature. A magnetic monopole would be different. It would carry only a north pole or only a south pole, a single magnetic charge on its own. The idea of such particles has been around for about a century, but it took on a precise form when physicist Paul Dirac showed in the early 1930s that the existence of even one magnetic monopole in the universe could explain why electric charge comes in neat units. The fact that the charge of the electron and the proton are exact, matching opposites, is one of those quiet miracles of physics. Dirac's work suggested that a lone magnetic monopole somewhere in the cosmos could account for this quantization in a natural way. Later, grand unified theories, which try to merge the electromagnetic force with the weak and strong nuclear forces into a single framework, predicted that magnetic monopoles might have been created in the early universe during high-energy phase transitions as the unified force split into the separate forces we know today. the fields involved could have formed knots and defects. Some of these defects, according to the theory, would behave as magnetic monopoles, isolated carriers of magnetic charge, frozen relics from a time when the forces of nature were arranged differently. If monopoles exist, they are expected to be extremely massive compared to familiar particles like electrons or protons. That enormous mass means they would be very hard to produce in any human-made accelerator, even in machines as powerful as the Large Hadron Collider, the LHC. They would also be rare and interact only weakly with ordinary matter, able to pass through vast amounts of material without leaving a strong trace. All of this makes them very difficult to find. Still, the search has been going on for decades. Some experiments have placed large detectors underground or in quiet environments, hoping that a passing monopole would leave a distinctive magnetic signal as it moved through. Others have combed through data from cosmic rays, the high-energy particles that constantly rain down on Earth from deep space. If monopoles were created in the early universe and survived until now, some might drift through the galaxy, occasionally passing through our instruments. So far, no unambiguous, universally accepted detection has been made, but the possibility remains open. If magnetic monopoles were ever found, it would be a profound moment. They would constitute an entirely new class of particle, not included in the standard model of particle physics as we currently use it. Their discovery would force us to revise that model and would strongly support the idea that, at very high energies, the forces of nature are unified. In other words, a single, solitary magnetic charge could point straight back to the conditions that reigned in the first instance after the Big Bang. There is also a quieter, more structural question. If monopoles were born in the early universe, where would they be now? Because they are heavy, gravity would have had a long time to act on them. Over billions of years, they might have drifted into the deeper gravitational wells carved out by galaxies and clusters. Regions of higher density, where matter has gathered most strongly, would be like basins where such particles could slowly collect. In that picture, monopoles might be more common near the centers of massive structures, in galaxy clusters, along the densest parts of the cosmic web, or near supermassive black holes where gravity is fiercest. If they truly exist, they might be hiding where the universe's mass has pooled most deeply, drawn in by the same gravitational pull that gathers stars and dark matter in the central regions of galaxies and in the crowded hearts of galaxy clusters where the gravitational forces are strongest. In those deep, massive regions of the cosmos, the crowded hearts of galaxies and galaxy clusters, gravity acts like a slow, patient sink. Over billions of years, it pulls in not just stars and gas, but also dark matter, and, if they exist, more exotic travelers like magnetic monopoles. A lonely monopole drifting through space could be captured by these heavy hubs, gradually building up a denser population near galactic cores, cluster centers, and the deepest wells of the cosmic web. If we were ever able to detect monopoles in such regions, their presence would tell us more than just they are real. They would trace where mass has gathered most strongly, sketching out the hidden architecture of dark matter and the way gravity has sculpted structure on the largest scales. Their distribution could reveal which parts of the universe have been acting as long-term collectors of exotic particles. Some physicists imagine an even richer picture, where monopoles are not just sprinkled randomly, but guided by ancient features of space-time itself. During the early universe's phase transitions, as the fundamental forces separated from a more unified state, The fields that fill space may have developed knots and seams, known as topological defects, things with names like cosmic strings and domain walls. If such defects formed, they could have acted like rails and catch points, concentrating monopoles along lines or sheets in space rather than spreading them out evenly. Mapping monopoles, if we ever manage it, could therefore become a way of mapping the deep texture of space-time, frozen in from the universe's earliest moments. Their role would not end with their birth. If monopoles are pulled toward dense regions, they might take part subtly in the ongoing life of galaxies and clusters. They could interact with magnetic fields, tweak the motion of charged particles, or influence how gas behaves near powerful fields and shocks. All of this remains speculative, but even the possibility hints at new layers in the story of how cosmic structures evolve. Because monopoles are tied so closely to symmetry and unification, discovering them would also shine light backward in time. Their masses, charges, and locations would carry clues about what the universe was like just after the Big Bang, when forces were still merging and separating. In that way, each monopole would be a tiny, solid fossil from an era we can otherwise reach only through equations. From these hypothetical magnetic relics, the story drifts to another kind of almost invisible messenger, one that we know for certain exists and that is constantly passing through us: the neutrino. If monopoles would be rare, neutrinos are the opposite. Trillions of them slip through your body every second, silently crossing Earth, the atmosphere, and the space beyond, almost never touching anything at all. Neutrinos belong to the lepton family of particles, alongside electrons and their heavier cousins. For a long time, they were thought to be massless, but experiments eventually showed that they do have mass, so small that it is difficult even to express. They come in 3 flavors: electron neutrinos, muon neutrinos, and tau neutrinos, and they have the strange habit of changing from one flavor to another as they travel, a quiet shape-shifting that tells us their properties are deeply woven into the fabric of fundamental physics. What makes neutrinos so special for astronomy is their shyness. They interact only through the weak nuclear force and gravity, so matter is almost transparent to them. While photons are easily absorbed, scattered, and blocked by gas, dust, and dense matter, neutrinos can stream straight through the cores of stars, across whole galaxies, and through thick layers of rock or ice. A single neutrino could cross a wall of solid lead, many light years thick, and still emerge untouched on the other side. This near invisibility is a curse and a gift. It makes neutrinos incredibly hard to detect, but it also allows them to carry unspoiled information from places that light cannot easily escape. In the heart of the sun, for example, nuclear fusion converts hydrogen into helium, releasing energy in the form of light and neutrinos. Photons that come from the core bounce around inside the sun for a very long time before finally escaping from the surface. Neutrinos, on the other hand, fly outward almost immediately, slipping through the solar material as if it were barely there. When they reach Earth, they bring a direct report from the sun's core, allowing us to test our models of stellar fusion and see whether the sun is behaving as we think it should. Huge detectors have been built to eavesdrop on these ghostly particles. Some are deep underground or buried beneath mountains. Others, like the Super Kamiokande experiment in Japan, fill enormous tanks with ultra-pure water and surround them with sensitive light sensors. The IceCube Neutrino Observatory at the South Pole uses the Antarctic ice itself as a detector, with strings of sensors lowered into the clear, ancient ice. When a rare neutrino does happen to collide with an atom in these vast volumes, it can produce a charged particle that moves faster than light can travel in that medium. This creates a faint cone of blue light called Cherenkov radiation, which the detectors can see. From those brief flashes, scientists reconstruct the direction and energy of the incoming neutrino. Neutrino astronomy truly came to life when detectors caught neutrinos from a nearby supernova, the explosion of a massive star. In the event known as Supernova 1987A, in the Large Magellanic Cloud, a handful of neutrinos arrived at Earth shortly before the first visible light from the explosion. They had escaped directly from the collapsing core, announcing the star's death before its outer layers had time to brighten. That detection confirmed many theoretical ideas about how stars die and showed that neutrinos carry a huge fraction of the energy in such cataclysms. Today, neutrino observatories also look beyond our local neighborhood. They search for high-energy neutrinos coming from active galactic nuclei, galaxies whose central supermassive black holes are feasting on matter and flinging out jets of particles and radiation. In those violent environments, collisions and shocks can accelerate particles to extreme energies, and neutrinos produced there can escape, traveling across vast distances to reach us. By tracing these high-energy neutrinos back to their sources, scientists hope to understand how supermassive black holes grow, how they influence their host galaxies, and how the most energetic particles in the universe are born. There is an even more ancient neutrino background as well, a relic from the Big Bang itself. Just as the cosmic microwave background is a bath of ancient photons released when the young universe cooled enough for light to travel freely, there should be a cosmic neutrino background, a sea of primordial neutrinos left over from an even earlier time. These neutrinos are now extremely low in energy, spread thinly through space, and incredibly difficult to detect. But if we ever managed to measure them, they would give us a direct glimpse into conditions only seconds after the universe began, when temperatures and densities were far beyond anything we can reach in laboratories. Because neutrinos respond to gravity but interact so weakly with matter, they might also help map the distribution of dark matter. Dark matter does not emit or absorb light, but its gravity shapes the motion of stars and galaxies and bends the paths of light traveling near it. In regions where dark matter is densest, the way neutrinos move and cluster could carry subtle signatures. In that sense, neutrinos could become guides through the dark, tracing the invisible scaffolding that supports galaxies and clusters. There is even a quiet possibility that neutrinos could help answer lingering questions about whether the universe has any hidden central structure or particularly special regions. The standard cosmological model says that, on the largest scales, the universe should look the same in every direction, with no privileged center. But if there were any deep asymmetries tucked inside the cosmic web, neutrinos, with their ability to travel straight through dense matter, might be among the few messengers able to reveal them. Differences in the patterns of neutrinos arriving from various directions, or subtle variations in their energies and flavors, could hint at structures that light cannot easily probe. As we listen to these ghost particles and trace the paths of exotic objects and fields, another idea waits at the edge of thought, asking us to reconsider the story of time itself. Instead of a universe with a single birth and a one-way journey toward a final fate, the cyclic universe picture imagines something more like breathing. In that view, the cosmos does not begin once and expand forever. It goes through repeated cycles of expansion and contraction, with each Big Bang leading to growth and each eventual Big Crunch setting the stage for another beginning. In such a rhythm, there is no ultimate first moment and no final last one, only an endless series of cosmic renewals, each new universe rising from the traces of the one before. In the gentle rhythm of the cyclic universe picture, the Big Bang is not a single, lonely drumbeat, but one note in an endless song. In this view, the universe expands for a long, bright season after a Big Bang, galaxies drifting apart and structures unfolding. Then, slowly, the pull of all the matter and energy begins to win against the outward rush. Expansion slows, pauses, and finally reverses. The universe starts to fall back in on itself. As this contraction continues, galaxies, stars, and all the vast scaffolding of the cosmos are drawn closer and closer together. Temperatures rise, densities climb, and everything that was once spread over unimaginable distances is compressed into a smaller and smaller volume. In the most dramatic version of this story, the universe ends in a big crunch, a collapse into a state so dense and hot that it resembles, in many ways, the conditions that existed just before a Big Bang. From there, the picture proposes a bounce. Instead of remaining trapped forever in a final singularity, the universe rebounds. The extreme compression at the core becomes the seed of a new expansion. Space stretches again, cooling and thinning as new galaxies, stars, and planets take shape. In this way, every Big Crunch becomes the doorway to another Big Bang, and the cosmos moves through a chain of cycles, each one giving rise to the next. At the heart of this idea is a kind of cosmic core, not a place you could point to with a telescope, but a state the universe passes through. As everything contracts, matter and energy are drawn into a region of extreme density, a focus where space-time itself is crushed into something like a single, shared moment. Some theories imagine this core as holding traces of previous cycles, tiny imprints that influence what the next universe will be like. In that sense, each new expansion is not entirely detached from what came before. It carries subtle echoes of earlier worlds. This cyclical picture changes how we think about beginnings and endings. Instead of a universe that starts once in a burst of fire and ends once in a slow fade into cold darkness, the cosmos becomes an ongoing process of renewal. Galaxies form, age, and dissolve. Stars are born and die. Life may arise and vanish again and again over cycles that stretch far beyond any individual story. Time, in such a universe, does not have a single starting line or a distant finish, but loops softly, with each cycle both new and deeply familiar. Still, the cyclic idea faces a quiet challenge from what we see today. Observations suggest that the expansion of the universe is not slowing down. It is speeding up, driven by dark energy. In the standard picture, this leads to a future where galaxies grow forever, more distant, stars burn out, and the universe drifts toward a thin, cold state. In that fate, there is no big crunch, only a slow slide into what is often called heat death. Some cyclic models answer this by giving dark energy a changing role. In these versions, dark energy may eventually weaken, transform, or even reverse its effect. The acceleration could slow, stop, and then turn into contraction, allowing gravity to gather everything back in. Other models, inspired by string theory, imagine our universe as a three-dimensional brain living inside a larger, higher dimensional bulk. In those sketches, two such brains can drift, approach, and collide. Each collision releases energy, showing up to us as something very much like a Big Bang. After the collision, the brains move apart, the universe expands and evolves, and over immense times the brains drift back together to collide again. In that picture, the cycles are driven not just by gravity in our universe, but by the motion of higher dimensional structures we cannot directly see. While these ideas trace the rhythm of the whole cosmos, our own galaxy is caught in a more local dance. In a particular direction in the sky, at distances of roughly 1 to a few 100 million light years, lies a massive region whose gravity tugs noticeably on nearby galaxies, including our Milky Way. When astronomers measured how galaxies in our neighborhood move, they noticed that they are not simply being carried along by the general expansion of space. They also have a peculiar motion, a drift toward a certain patch of sky, as if an unseen hand were gently pulling them. This mysterious influence is often called the Great Attractor. It is not a single object, like a lone black hole, but more likely a dense concentration of matter clusters, of galaxies, rivers of dark matter, and hot gas all piled together to create a strong gravitational well. The pull is so large that it affects entire superclusters of galaxies, giving them additional velocities of several hundred kilometers per second toward that region. Studying the Great Attractor is difficult because much of it lies behind the crowded plane of our own galaxy, a swath of sky sometimes called the zone of avoidance. Dust, gas, and countless stars in the Milky Way block our view in visible light. To peer through this curtain, astronomers use radio waves and X-rays, which pass more easily through the obscuring material. These observations reveal galaxy clusters, such as the Norma cluster, that sit in the direction of the Great Attractor and contribute to its gravitational pull. Dark matter, that invisible mass that does not shine or absorb light, likely plays a major role here. Because dark matter makes up the majority of the matter content of the universe, any deep gravitational well is almost certainly supported by a heavy dark matter halo. The Great Attractor region probably contains a large amount of dark matter wrapped around its visible galaxies, creating a gravitational anchor that tugs on structures over vast distances. Yet the Great Attractor may not be the end of the story. Beyond it, farther out in the same general direction, lies an even more massive gathering of galaxies known as the Shapley Supercluster. Some studies suggest that our local flow of galaxies may be influenced not only by the Great Attractor, but also by this larger structure, and perhaps by other concentrations of matter still farther away. If so, what we call the Great Attractor might be just one node in a much wider network of gravitational pulls, all woven into the cosmic web. These deep wells of gravity invite another speculative thought. If galaxies are anchored by supermassive black holes at their centers, could still larger scales be influenced by even more massive black holes? We already know that the Milky Way hosts a supermassive black hole called Sagittarius A star, with a mass around 4 million times that of the Sunday. Many other galaxies harbor similar or even larger black holes, which act as gravitational hubs, shaping the orbits of nearby stars and regulating activity in their central regions. Some have wondered whether there could be black holes on higher rungs of this latter object so massive that they influence not just a single galaxy, but clusters of galaxies or wider regions of space. The idea of a truly central black hole for the entire universe does not fit comfortably with the cosmological principle, which says that on the largest scales, there is no special point or preferred direction. There is no observational evidence for a single universe-spanning black hole that sits at an absolute center. Still, the notion is a useful lens for thinking about how gravity organizes structure. On every scale, we can clearly see from planets to stars, from stars to galaxies, from galaxies to clusters. Mass tends to gather around deeper wells, and motion is shaped by these hidden depths. If, in the crowded hearts of superclusters, or along the densest knots of the cosmic web, there exist black holes more massive than any we have yet observed, they would act as powerful anchors. Their gravity would help draw in surrounding matter, influence the growth of galaxies, and contribute to the sculpting of the vast network of galaxies and dark matter that spans the universe. If black holes can anchor galaxies, it is natural to wonder what would happen if there were one so enormous that its gravity tugged not just on a single galaxy or even a cluster, but on whole regions of the cosmic web. In that quiet speculation, some people imagine a central black hole so massive that it could help shape the large-scale flows we see, the slow drift of superclusters across hundreds of millions of light years. For comparison, think of one of the largest black holes we know, a quasar, often called TON 618, whose central black hole is estimated to be around 66 billion times the mass of the Sunday. Even that giant would be tiny next to what would be required for a truly universe-anchoring black hole. Such a hypothetical object might need to have a mass measured in trillions of suns or more, an almost unimaginable concentration of gravity. If something like that existed, it would not just be an oddity, it would be a dominant presence, quietly steering the motion of vast structures. But here the picture runs into a deep feature of our best cosmological models. On the largest scales, the universe seems to follow the cosmological principle. It is roughly homogeneous and isotropic, meaning that, averaged over enough distance, it looks the same in every direction and in every place. There is no special location that stands out as more central than the others. The expansion of space happens everywhere at once, not from a single favored point. In that kind of universe, the idea of one true central black hole, sitting at an absolute core, loses its footing. There is no single middle for it to occupy. Even so, the idea of a gravitational anchor does not have to be thrown away. It simply shifts to more modest scales. In a galaxy cluster or a supercluster, there could, in principle, be black holes more massive than any we have yet confirmed, sitting near the densest knots of matter. Their gravity would not rule the entire universe, but it could influence the local cosmic neighborhood, guiding the motion of nearby galaxies in subtle ways. In that sense, the pattern we see in galaxies, each one with a supermassive black hole at its heart, might echo upward, with larger structures harboring proportionally larger anchors. If such ultra-massive black holes exist, we would expect them to leave fingerprints in the motions around them. Just as astronomers infer the presence of a black hole at the center of a galaxy by watching stars and gas orbit at unexpected speeds, they could look for large regions where galaxies seem to fall toward an invisible focus. By measuring red shifts and blue shifts, the tiny changes in light that reveal whether something is moving away or toward us, and by mapping how those motions are arranged on the sky, we might catch a glimpse of a shared pull that cannot be fully explained by the average expansion or by known clusters alone. Gravitational lensing would offer another clue, a mass that enormous would bend the paths of light passing nearby, distorting the images of more distant galaxies behind it. Even if the black hole itself were invisible, the way background light is stretched, brightened, or multiplied could betray its presence. And if matter were falling into such a giant, the swirling gas in an accretion disk could heat up and glow in X-rays or gamma rays, sending out a high-energy beacon from a region with no obvious visible source. Together, these hints could point to something vast and hidden. Whether or not such extreme anchors exist, they do not answer the deeper question that lingers underneath. Where is the center of all this? If space is expanding, is there not some special point from which everything is moving away? Our intuition, shaped by fireworks and ripples in water, wants an explosion in a pre-existing space, a single origin point from which matter flies outward. The Big Bang, though, is not that kind of explosion. It is not a ball of stuff expanding into a larger room. It is the expansion of space itself. A gentle way to picture this is with the surface of a balloon. Imagine tiny galaxies drawn on the rubber. As you blow air into the balloon, the surface stretches, and every galaxy moves away from every other. There is no special dot on the surface that you can point to as the center of the expansion. The center of the balloon lives in a higher dimension, inside the volume of the balloon, not on its skin. For the two-dimensional creatures living on that surface, there is only the stretching, everywhere at once. Our universe is like that, but in 3 dimensions. The Big Bang was not one point in space that exploded. It was the moment when space itself began expanding. As time has passed, the average distances between galaxies have grown because the fabric of space is stretching, not because everything was hurled outward from a single spot into a pre-existing emptiness. In this sense, every location takes part in the expansion. Every region sees its neighbors drifting away. On very large scales, observations back this up. When astronomers map galaxies across billions of light years, they find that while there are clusters and voids and filaments, the overall pattern is surprisingly uniform. There is no unique direction where everything is denser or more special. This large-scale homogeneity and isotropy mean that no place can be singled out as the one true center. It is also tempting to imagine the universe expanding into something as a balloon grows into the air around it. But in our best descriptions, the universe is not growing inside a larger space. The universe is the totality of space and time. When we say it is expanding, we mean that the distances measured within it are increasing. There is no outside that it needs to grow into, just as the two-dimensional surface of the balloon does not need a two-dimensional exterior in order to stretch. Part of the confusion comes from how we experience our own vantage point. From here on Earth, it looks as though everything is moving away from us. The more distant a galaxy is, on average, the faster it recedes. That can make it feel as if we are sitting at the center of an expanding bubble. But if you were to stand in a galaxy billions of light years away and repeat the same measurements, you would see the same pattern from there. Galaxies in all directions would, on average, be moving away from you as well. Every observer, wherever they are, sees themselves at the center of their own observable universe. The observable universe is simply the region from which light has had enough time to reach a given observer since the Big Bang. Because light speed is finite and the universe has a finite age, this region is always limited. For someone in another galaxy, that bubble is centered on them instead of us. Each bubble overlaps with others, but there is no global, preferred center that all observers would agree on. The balloon analogy can help here too. Imagine you are a tiny ant on the surface as it inflates. You watch other ants moving away from you in all directions and think, I must be at the center. But if you could talk to another ant far away, they would report the same thing. From their perspective, you are the one drifting away. Neither of you is at a privileged center. You are both simply riding the same stretching surface. Now extend that idea to a space that might be infinite, or at least much larger than anything we can see. An infinite space has no middle. Even if the universe turns out not to be truly infinite, but just very large, the way it expands still does not pick out a unique central point. The stretching happens everywhere. Galaxies are carried apart like dots on the balloon, with no special dot crowned as the origin. From where we stand, it is easy to feel as though our own observable universe, the bubble we can see, is all there is, and that we occupy its center. But that is more a reflection of perspective than of deep structure. On the grandest scales, every point in space is part of the same expansion, and no location is more at the heart than any other. So when we ask, where is the center of the universe? The gentle answer is that the question does not quite fit the reality. In a universe where space itself is stretching, and where the large-scale pattern looks the same in every direction, the idea of a single, fixed center simply falls away. Instead, we are left with something quieter and in its own way more comforting, a cosmos in which every place shares equally in the unfolding, where each galaxy, each cluster, each lonely patch of intergalactic dark is part of the same grand movement, carried along together in the ongoing expansion of space.